All right. Okay. Now, first off, I want to review some basic concepts regarding statistics and whatsoever. And this will be the first chapter, and this is about the introduction. Okay, so this is the introduction. And there was a subchapter, and this is called random variables. Okay. Now, guys, what is a random variable? Basically, what you have is the following setup. Okay, so here you have basically. I'm not going to go into detail. Okay, so but basically, what you have is the sample space. Okay, and the sample space contains. Okay, so the notation for that is omega. And a sample space contains all outcomes of a random experiment. Okay, so this contains all outcomes, all possible outcomes, let's say. Okay, of a random experiment. Okay, so this is a sample space. Okay. All right. So now, of course, I mean, if you have a sample space, and then what the random variable is, and this is quite obvious here. Okay. So I'm not going to use the stuff from the measure theory because it's quite complicated. But the random variable is basically a real number. Okay. That depends on random. That's it. Okay. So the notation for that is this. Can you read this basically? Is it okay? More or less. I mean, if not, you should tell me. Okay. So here it says sample space. I can write it like this. Maybe I can sit down. It's easier. Okay. Then I don't want. Well, this is like kind of weird. But anyway. Okay. So here the random variable I call is capital Y. Okay. So here you have the random variable which is called capital Y, and you have a function that goes from the sample space to the set of real numbers. Okay. So basically, again, so suppose that, for instance, you have, let's say, the sample space, okay, contains of the elements omega 1, omega 2, omega 3, and so forth, okay? And then, of course, you have, let's say, the function, which is the random variable, depending on the outcomes of the random experiment, okay? So basically, so this is the image, okay? So here you have the image of the outcome omega 1, okay? So from a theoretical standpoint. And the image is, of course, a real number. Okay, so this thing is, of course, a real number here. Okay, so this is a real number. That depends on the outcome of the random experiment. Okay? And any real number that depends on the outcome of a random experiment is called a random number. Okay, random variable, let's say. Okay? Is that okay? Now, I don't go any further than this, okay? So probably you've seen all of this stuff regarding measurability and all these kind of things, but regarding sigma algebra, but we don't need this, so you're not gonna consider that. Okay, so this is basically a random variable. Now, there's a distribution related to each random variable, and the distribution of the random variable can be characterized by the distribution function. Okay, so I'm gonna use this as a definition. Sorry, I used, accidentally I used X here, and I'll call this Y. Okay, it's supposed to be Y as well. Okay, I apologize. Okay, so this is the image of the outcome. So basically, I apologize, I used Y for the random variable, not X. Okay, now basically what you have for the distribution function, okay, so this is called the cumulative distribution function of the random variable. Okay, distribution function, okay, I use capital F sub y, okay, so of the random variable y, basically, is a function, okay, that gives you, so this is going to be at point k, let's say, alright, so here you have the function at point k, that will give you the probability that the random variable is less than or equal to k, okay? You all know this, okay? So probably this is something you have already seen. So this is called the probability, or this is the probability measure, okay? And probability of what? The probability of the corresponding event, Okay, so probability basically of the event that the random variable is less than or equal to k. Okay, so this is what you're talking about here. You understand this notation? Okay, so this is the corresponding event that we're looking at. Okay, so the probability of that event, and this is what the cumulative distribution function is giving you. Okay, now if you know basically the cumulative distribution function of a random variable, then you know everything about the distribution of the random variable. Okay, so this is the most important part. Okay, maybe you have seen this probably, right? So for instance, just let me give you a little example. Okay, so suppose that you have a following random variable, let's say, for which the probability is equal to 1, let's say is equal to 0.5, the probability that the random variable is equal to 2, let's say is 0.3, and the probability that the random variable is equal to 4, let's say is equal to 0.2. Okay, now what would be the distribution function of that? I mean, you can imagine that maybe that the distribution function at point 1 is basically the probability that the random variable is less than or equal to 1, which is of course obviously 0.5. Okay, less than or equal to 1. The realizations are 1, 2, and 4. Okay, so the random variable cannot be less than 4. So here, of course, the distribution function at point 1 is going to be equal to 0.4. Now, the distribution function, 0.5, sorry. The distribution function of the random variable at point 2 is going to be equal to the probability that the random variable is less than or equal to 2. And basically, this is the sum of the corresponding probabilities that you have here. So this is going to be 0.5 plus 0.3. Again, because less than 2, less than or equal to 2 means either 2 or less. Okay, so these are the 2, this is the 1, and these are the 2 realizations that are for which the corresponding condition is satisfied. Okay, so basically here you're going to have that the distribution function is equal to 0.8 at that point. And a distribution function of the 0.4 is equal to the probability that y is less than or equal to 4, so this is going to be equal to 1, of course. Okay, again, the probability that y is less than or equal to 4 is equal to 1 because all realizations of the random variable are less than or equal to 4. Okay, so the outcomes of the random variable or the possible images, okay, so these are called the realization. Okay, so you can also call it, this is the realization. Okay, this is what I'm talking about here. Okay, so here you have the possible realizations. You have 1, 2, and 4. These are the possible values that the random variable can take. Okay, so and basically this is quite simple, guys. For instance, the distribution function at point 5. Again, of course, 5 is not the realization of the random variable, but the probability that the random variable is less than or equal to 5 is also equal to 1. Okay, because all realizations of the random variable are less than or equal to 5. Or, for instance, the distribution function at point 0 is going to be equal to the probability that y is less than or equal to 0, which is, here again, here is 0, because none of the realizations of the random variable are less than or equal to 0. None of them. So the probability that this occurs is 0, right? Okay, so basically this is how it looks. Now, what would be the generalization of the distribution function here in this case? The generalization of the distribution function would be, and this is something that you're going to get here. Now, the possible values of the distribution functions are 0, of course, and then you have 0.5, then you have 0.8, and then you're going to have 1, right? That these are the possible values that the distribution function can have. Okay, so when is a distribution function is equal to 0? The distribution function is equal to 0 if the argument of the function is less than or equal to 1. Okay, so if k is less than, if k is just less than 1, not equal to 1, because if k is equal to 1, then the distribution function at point k will be equal to 0.5 as we have seen this here. Okay, so for the arguments being less than 1, the distribution function is equal to 0. Now, the distribution function is equal to 0.5 if the argument is equal to 1, but not just for 1. For instance, 1.5 would be also the same thing, right? Because the probability, let's say, the probability that y is less than or equal to 1.5 is also equal to 0.5. Again, Okay, the probability of the event that the random variable is less than or equal to 1.5 is the same thing as the probability that the random variable is less than or equal to 1, because only the realization 1 is less than or equal to 1.5, and that's the only thing that remains. So here you're going to have that the distribution function is equal to 0.5 for k's, okay, that are between 1 and 2, where basically you have that 1 is, I mean, you can see this here, okay, so 1 is included here in this section, but 2 is not, because the distribution function at point 2 is equal to 0.8, of course, okay? So this is what you have here as well, okay? And here this goes from 2 to 4, okay, where, of course, 4 is excluded here from this range, and the distribution function is equal to 1 for input arguments that are greater than or equal to 4. Okay, so this is how the distribution function looks. Okay, for this type of random variable. Okay, now guys, there are two random variables to distinguish from, and the ones are the discrete ones, and the other ones are the continuous ones. Okay, so I'm not going to go into details about what about that, but basically, what is a discrete random variable? Okay, so this would be the definition. Okay, you're supposed to know this. Okay, now a random variable is called discrete. Okay, is called discrete. Okay, if its realizations can be written as a sequence. Okay, and so if its realizations can be written as a sequence. Okay, can be written by means of a sequence. Okay, so by a sequence. Now, if that's the case, that you can write the realization of the random variable as a sequence, then this means that basically that the realizations are countable. So this is the property. I'm not sure whether or not you already attended the previous mathematics course, which was lectured by me as well, but this is the so-called countability property. Okay? Okay? So a set is called countable if, let's say, its members or its elements can be written as a sequence. Okay? A sequence has the members and the set has the elements. Okay? What do I mean by that? For instance, I'm going to give you an example. For instance, let's say the number of failed trials until, let's say you throw the dice, the number of failed trials until the number 6 comes. Okay, so let's say you have the random variable. Okay, so y denote the number of failed trials. Okay. Okay. Okay, so number of failed trials until a certain event occurs. For instance, the number of failed trials until, let's say, you throw the dice and you get the number 6, right, appearing on the dice. Okay, and you count how much you have thrown the dice, how many times you've thrown the dice, and regarding the number of failed trials will be actually the realization of the random variables. Okay, now the realizations, or the set of realizations. Okay, so the set of the realizations, okay, or the images, let's say, or the realizations, okay, of y, of course, are going to be, or is going to be, as follows. Okay, so if, let's say, if you take the dice and you throw it and the number 6 appears for the first time, then your number of failed trials will be equal to 0, right? Then if, let's say this is not the case, so you take the dice for the first time and you throw it, and you don't have 6, then of course you take it for the second time, so then you can throw it, and let's say it appears on the second time, so then of course the number of failed trials is equal to 1. Okay? Now this can go on, right? So basically, I mean, let's say you throw the dice, it doesn't appear again, so you throw the dice for the first time, you don't get 6, you throw the dice for the second time, you don't get 6, but you throw the dice for the third time, so then if you get 6 for the third time, okay, so then of course the number of failed trials is equal to 2, and so forth. Okay, so basically what you have is that the number of failed trials, the set is not finite. Okay, okay, so the set is not finite. So you have infinitely many realizations, because guys, there is no guarantee, let's say, that I mean, for instance, if you throw the dice 100,000 times, okay, that the number 6 will appear. There is no guarantee for that. You understand? I'm not saying that this is likely the case. Okay, so most cases you're gonna have that. But I mean, from the theoretical perspective, the probability that this happens, okay, so suppose that you throw the dice 100,000 times and the number 6 doesn't appear, not once, okay, the probability for that is greater than 0, okay? I mean, obviously, right? It's not much greater than 0, but it's greater still, okay? So there is no guarantee for that. So since there is no guarantee for that, the number of realizations is not finite, but still there is a possibility you have a sequence here. Okay, so this is a sequence, right? So this is basically, you have a sequence still. So there is a possibility to write the realizations of the random variables as a sequence, even though the realizations are not finite. So in this case, the random variable is called discrete. Okay, so y is discrete. Okay? You understand? Okay? So in case the random variable is discrete, then basically the distribution function can be written as follows. Okay, so this is going to be something that I would like you to add here. So if, let's say, if the random variable is discrete, then the distribution function, okay, so its distribution function can be written as, okay, and it can be written as follows. So you're going to have that here. So this is going to be, let's say, f sub y, okay, at point k. K is the argument, okay, so that you're looking at, and this will be represented by the following sum, okay. So let's say you have, for instance, I mean, assuming that you have these realizations, okay, so you have, let's say, p of y being less than or equal to, let's say, yi, okay, so this is the precise notation, okay, and for yi, so these are the realizations, okay, so yi is being less than k, so for all yi that are less than k, okay, you sum up the probabilities, and this is what we have done, right? So for instance, here in the previous case, right, remember that I introduced you to that example. Okay, basically what you can do here and assume that, okay, so the realizations, okay, so I will tell you here, so where I will leave a little space here maybe, so I will add here something to it, okay, so where, of course, y1, y2, y3, and so forth are the realizations, okay, of the random variable y, okay, obviously, okay. So for all realizations for which the condition holds that is less than or equal to k, what you actually do is to sum up the corresponding probability mass function, guys. This is called the probability mass function, okay. So here you're going to have the same thing. So basically, so here yi less than or equal to k, okay, and I'm going to call this function small f here, okay. So you have f sub y at point yi, okay. So basically this is what you're going to look at. Now this function here is called the probability mass function, okay. Okay, so we'll continue here, and fy is the probability mass function. This is the probability mass function of the random variable, capital Y. So basically, I mean, if you want to know what it is, this is relatively easy. So you don't need to know this. Okay, so you have, let's say p of y being equal to 1 is equal to 0.4, p of y being equal to let's say 0.5, it was in the previous case, 0.3, and p of y being equal to 4, let's say this is 0.2. Then, of course, the probability mass function of y at point k, let's say, is going to be either 0.5, okay, for k being equal to 1. It's going to be 0.3, for k being equal to 2. it's going to be equal to 0.2 for k being equal to 4, and of course it's going to be equal to 0 otherwise. So in all other cases, okay? So that's how the probability mass function works. Okay, so otherwise. I'm sure you're probably familiar with this. You remember that, guys? Okay? I will come back to it quite often, so I need to make sure that you're aware of this. Okay? Of course, I assume that you've seen this, but it might not be clear. All right? Okay? Is this clear? Now, what is a continuous random variable? And I'm gonna introduce it to that because here probably you've seen this in the previous example. Okay, so let's consider the distribution function here again. So let's say how the distribution function looks like. Okay, so here you had 0, you had 0.5, here you had 0.8, and here you had 1. So 0 for k was equal to less than 1, 0.5 for k being between 1 and 2. Okay, where of course 1 is still included in there. Okay, so we already talked about it, right? This was the case for the last one, and okay, again, so this is the distribution function. All right, so this is the probability mass function, or you can say the probability function for short, and this is the distribution function, cumulative distribution function, you can say distribution function for short. Now, how does a distribution function look like? How does it look like? Now, first off, I mean, you have to see this here, okay? So basically, I mean, this is, let's say this is a distribution function. Okay, so here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so here 1, 4.5. Okay, so here the distribution function is 0. Okay, so here 1, 2, 3, and 4. The distribution function is 0. Okay, for k being less than 1. So here you have this part. Okay, so this is how the distribution function looks like. Okay, but it doesn't. I mean, it approaches 1, but it's not there, right? So therefore, you have to symbolize that by using this hole here. And 0.5, you have 0.5 starting here, okay, to 2. Okay, so because if you put 1 into the function, then you get 0.5, so it's going to be here, okay? And the hole is here, so here the function, let's say, is empty. All right, and 0.8 is going to be here. Right? Okay, here's the hole, and from this point here, okay, it's going to be equal to 1, so it's up there. Okay, so this is how the distribution function looks here for this distribution, and you can clearly see that the distribution function is not continuous. Okay, so basically f is not continuous. Okay. Why? Because the left and the right side limit of the functions are not equal, obviously. Okay, so here, for instance, the left-sided limit here is equal to 0, and the right-sided limit at point 1 is equal to 1. Okay? All right, you see this? So if you, let's say, if you approach the distribution function, okay, for, let's say, k approaches 1 from the left, then it's going to be equal to 0, and the limit of the distribution function, if you, let's say, if k converges to 1 from the right, it's going to be 0.5, so these two are not equal. Okay, so then hence the function cannot be continuous. Okay, remember this. I mean, it's not continuous at that point at least, okay, but if you find one point for which the function is not continuous, then basically the whole thing is not continuous. All right? So now, what is a continuous random variable? I'm going to define a continuous random variable as follows. Okay, so a random variable is called continuous. Okay. Is called continuous if its distribution function, okay, if its distribution function is continuous. Okay, so basically, okay, so you don't have any jumps in there. stuff like that. Okay, so the random variable is called continuous if its distribution function is continuous. For instance, for the normal distribution, you have a continuous distribution function. Now, okay, now there are two sorts of continuous random variables. Okay, now let's say the distribution function is continuous. Okay, so let's say, for instance, I'm going to summarize this in an example. Okay, so basically you have. Okay, so if let's say fy is continuous. Okay. Okay. Okay, then you have two options. Okay. All right. So there is a term absolute continuity as again. Okay, so I'm not going to discuss about that. So if y is absolute continuous. Okay. Okay, I'm not going to discuss that, so maybe you can look it up because it's relatively complicated. Okay, so there is a distinction between absolute continuity and continuity. And let's say if y, okay, fy is not absolutely continuous. Okay, so then if y is absolutely continuous, then the random variable has a density. Maybe you've heard of that. Okay, so y has a density. Okay. And here in this case, if fy is not absolutely continuous, again, the term absolute continuity is a mathematical expression which is relatively complicated to define, so I'm not going to do this here. Okay. Then y does not have a density. Okay. 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 Now, for instance, a distribution which is a continuous distribution but it doesn't have a density function is, for instance, the Cantor distribution. So here, for instance, the normal distribution. Okay, so example, you're already familiar with the normal distribution. Okay, normal distribution. The normal distribution has a density. Okay, so you can, this is something that you probably are familiar with, but there are continuous distributions which do not have a density function. And for instance, an example, you can look it up if you like. An example includes the so-called Cantor distribution. Okay, so maybe if you want to look up the Cantor distribution, the Cantor distribution is a continuous distribution, so it has a continuous distribution function, but it doesn't have a density function. So if you see the example, then you might understand a little bit what absolute continuity means, okay, but we're not going to define this here. So maybe if you want to look it up, then you can look it up. So the so-called Cantor distribution is an example, okay, that relates to that, okay, but we're not going to consider that here. So, but I would expect you just for you to know that some continuous distributions have density functions and some don't. Now, we're not going to consider continuous distributions that don't have density functions, okay. So basically, we're only going to consider distributions or continuous distributions that do have density functions. Okay, so you can forget this, but if the distribution is continuous, it does not automatically mean that it has a density function. Okay, that's what I wanted to tell you here at this point. Okay, and a famous example is a Cantor distribution, but we're not gonna talk about it because this is much beyond the scope of this course. Okay. Now, I have to stop here, unfortunately. So tomorrow we're going to see each other in the computer room, right? So I'm going to teach you a little bit about computer techniques, whatever. For implementations, if you can do the programming, or if you have attended, let's say, for instance, a class, then you don't need to come, okay? So you don't need to come. If you have already used that for implementations, maybe in previous examples, but I wanted to teach you something about MATLAB, so then you'll be able to submit assignments in terms of these goals. Okay? So tomorrow we'll see you in a different lecture room. Okay. Thanks.